So I record. So I did start recording. So hello to everybody. That's a great pleasure to have this new workshop, this last workshop regarding the Python development in astronomy and spectroscopy. And so I let Matthieu present us the meeting today. Okay, thank you, Matthieu.
Okay, thank you, François. Hello, everybody. I start to share my screen. Okay. Okay. So let's go. So thanks for being here for the third workshop. The last but not least, we continue to browse the different uses related to the domain and start with Python. And the program of today is to show testimonials and to watch testimonial and examples of uses in Python. So we will see some great speakers, and we will start from the low level, from the materials, from hardware, and we go upper next to the hardware. In first, we will see Python low level with Raspberry Pi, command line, Aperry REST, Flask, with an illustration with the control of a telescope shelter by François Cochard. And after that, we will see remote observatory with Python with Thibault Notargiacomo. And we continue to go upper with real-time processing and display of a select acquisition of SER file. With Valérie Desnoux. And we will see after that PySer files reader library about manipulation of SER files also with Jean-Baptiste Buttet and Jean-Daniel Boutin. And we go again upper about UVEX database with Jupyter Notebook and Voila with Jean-Luc Martin. And I will finish this talk with automatic classification of H-alpha line profile for BE stars with AI. And I will make for real finish a conclusion about these 3 workshops about Python. So let's go for testimonials with François Cochard about his observatory.
Okay, thank you very much, Matthieu. So I will start on my side. I do share my screen, and I do have prepared some slides. I think normally you should see the first slide. Okay, so I'm really not a software developer. I'm not an expert in Python, but well, I like to play with these all these kind of things and all the small games that we have in hand. And I want to talk about some very low-level programming and with the Raspberry Pi with 2 different applications that I use at home. And I hope that quite soon that there will be the official product from Cheliac Instruments, which are the telescope shelter and the weather station. Okay, I want also to talk about the using Python of the Raspberry Pi, which is a wonderful small tool, and we'll talk about very quickly about multi-thread and real-time programming, and how can we interact with the script and between the scripts through the command line and the REST API. Just before I forget this, this is very important. You know that when you are doing this kind of stuff, it's important to have some mentors and some good friends that are experts, and you can ask as many questions as you want. And for me, I really want to thank you very much, Philippe de Vercher, who helped me a lot when developing these different applications. Also, Jacques Michelet, who is an expert in Linux and Python, and also Nicolas Durand. Nicolas is maybe not an expert in Python, but he's a software developer. He's working on the Demetra software, and he helped me to work on the structuration of the different programs. Okay. So here is the shelter I have in my backyard, and it's really close to me. It's at a few meters from where I'm talking to you right now. And this is a system that I've designed to make sure that the mission of this device is to protect the telescope inside. So in fact, I have a system which is very simple. I have one Raspberry Pi which is controlling the shelter and the weather station, which is important to control that we can observe in safe conditions. And I do have another Raspberry Pi who is hosting an indie server that controls all the instruments, so the cameras, the telescope, the mounts, the spokes for the calibration lamps, and so on. Okay, and the two systems are totally independent, and there is almost no link between two of them. So the shelter can decide to open or close whatever is the position of the telescope, and so on. Okay. The shelter is controlled by this box, and in this box you can see here the Raspberry Pi, okay, which is a small PC in fact, and we have designed an electronic board which is connected to the Raspberry to control the input outputs, and also we control the power supply, and we were able to switch to a battery in case of power cut. So we have all these features in around the Raspberry Pi. The Raspberry is really this is a real PC that runs under Linux. It is very cheap. It can work for 24 hours a day. I just checked before this meeting. Mine is running for more than 70 days at this moment, because we had a power cut a few weeks ago. And it is a really low power system. There is no hard disk running, so all the master storage is in the SD card here and the USB key here for the weather station database. So there is no part in movement, so it can really run for a long time. And it runs under Linux, and even for the latest version, you can run the Ubuntu distribution. And in any case, because you are running Linux, Python is already installed in any case. Okay. The structure is this one. I do have. So you have seen that there are 4 corners in the shelter, and for each corner you have a motor, and each motor is driven by an Arduino, an electronic card with an Arduino, small Arduino here, and a motor driver here. So you have the 4 motors that are driven, that are controlled by the Raspberry Pi here through an RS485 bus, which is a serial bus for which you can chain different devices. And I also have the weather station. So for the moment, it's very it's quick and dirty, and we'll do. I'll have it in much better shape in few weeks or months. I don't know, but I do have here the wind sensor, which is a static sensor. I do have several rain sensors. I like the redundance to make sure that I will not miss anything. And I do have this system which embeds a light sensor, an infrared sensor, and also temperature, humidity, and pressure. Okay, and all these devices are connected to the Raspberry with different ways. So the wind sensor is connected by the USB. This device is connected by your Wi-Fi, and the rain sensor are directly connected to the electronic board, additional board that we have. Okay, so it makes some. I like the system which is heterogeneous. So we have different kind of system, and we can really connect different kind of systems. When we do this kind of system, we need to have several scripts running in parallel. We have something a script which is watching at the weather. We have the scripts that are taking care of the motors, of the main control, and switching to the battery. We also have a script that is here to discuss with the user, and also, of course, all the scripts must talk to each other. For instance, if the weather is becoming bad, it gives the motors the order to close the dome. Okay, I want to show you very quickly, very basically, a few examples of the libraries that I use that are useful to do these kind of things. The first is the command line library, which is a CMD, and this is something which is very basic. So I will switch if it works. I hope that it works. Okay, so this is the script I use in a very basic text editor. Okay, and this is where I declare, yes, here we are. So I use well, at the beginning of the script, of course, I do import the module. I don't know where is the cursor. Here it is. So I do import the CMD library. Okay, and later on, I do start the declaration of a class which is based on CMD, and then I have defined some instructions, some commands. Okay, so for instance, I have open, close, go to, stop, and so on. These are all the commands I've defined for the shelter. Okay, and when all these functions are starting by do underscore, okay, that will not appear at the end, but I just have to declare that each command, and for each command I define a comment, a description of what it does, and the Python code for each of them, of course. And at the end of the script, I just have, if I can go down, when I start the script, so we do create all the different declare the different variables, and I just have to run this shelter.command loop, and then it will start, and from this point it will just wait for instructions for the user. How it works in real? Here is the what I've tested. So just before the meeting, I just run this line, so Python 3, and the shelter-control.py is the code that is here. Okay, so here I'm really connected by SSH, if you know that, to the Raspberry Pi. So this window is really the Raspberry Pi, which is running right now. First, I can ask for all the orders, all the commands. Okay, so and this is made automatically by the CMD library. So I can ask what is the list of the order that are available. We can see the open, we can see the stop, status, close somewhere, and so on. I can ask for help. If, for instance, if I ask what means help, what means close, it just displays what I've put as a comment in my code. Okay, so it's very useful. And then I can ask what is the status of the shelter. In this case, it gives me the position of each motor, and especially I know that in this position 1000 it is closed. And if I give the order to the shelter to open and ask for the status again, I will see that now the motors are moving. Okay, so if I look, I see the position of each motor permanently. Okay, and then I can do a stop. Okay, and if I do a stop, I see that now the motors are stopped and they remain at the same position. And now I can just ask, well, I could ask it to open, but I'm not sure that the weather is really perfect to observe tonight. Okay, so now I give the order. This is just to show you how it works, and it is very useful when you are doing this kind of script, when you just have to need some commands to talk to your system. And by the way, we are working right now on the motorization of the UVEX system, and I will use the same system as a first step to control the system. Okay. Now I come back to my presentation. There is something important also, is the multi-thread. I told you that when you have to make different scripts working in parallel, I would say that we have two options. well, you have much more in fact, but these are the one I want to present. The first one is to use the multi-thread. Multi-thread means that you can, in Python, you can run different threads in parallel within a same script. Okay, and for instance, for the shelter, this is very important because you have seen that we have two roofs, and we have the west and the east roof, and each of them is controlled by two motors. And in fact, I have one thread for each roof, and there is another thread that is asking permanently the position of each motor and the status of the shelter, and they are talking to each other, and we can even have some events, and you can have some log functions to make sure that we can synchronize the different threads. Okay, concretely how it works, if I go to this script again, I can see that at some positions I do have, let me, well, so this is, here it is. For instance, I have I declare a class which is based on a thread, or on the thread library. Okay, so this is for the roof control loop, and the roof control loop it means that I will have two instances of this class, one for the first roof and another one for the second roof. Okay, and I do declare, so this is a class in Python, so this is an object programming, and I do have some functions, okay, some methods inside this class, and at the end, I will start when I run the main program, which is usually at the end of the script. In fact, we declare the different variables, and I will just do that. So I will create an instance of the roof control loop. So one for the east and one for the west. Okay, and I just have to start them. Okay, and when they start, we run the different threads. Okay. So this is how it works, and then really they work in parallel. So inside the single script, you have different threads, and it helps to do some real-time control. The real-time control is something important in my case, because for a given roof, you have two motors, and if for any reason one of the motor is blocked, is stopped, it is important that I immediately stop the other motor, so there are stepper motor, to make sure that I will not damage, I will not bend the shelter. Okay, so it's important to have something not real time, not absolutely real time, but close to real time. Okay, the other option to make the different scripts working together is to use the REST API. So Matthieu already showed some things about this REST API last time, and in my case, this is very useful because this is a way for the different scripts to work and to talk together. For instance, I can ask for the weather. I do have a script for the weather, and I do have, in this case, I will define some. Yes, here it is. So I do declare some. I use the Flask library, as it was explained last time, and I define some URL or some HTTP request. It is close to the command line, in fact. And the difference is that I will not talk to the system through the command line, but I will send my orders through the web browser. Okay, and so in my case this is Firefox, but it can be any system. Okay, so the structure is almost the same. So I do define a certain number of commands, and I can access them by the system. And what is very useful in this case is that I can interact quickly with each script. For instance, well, in this case, if I look at my code, I see that I've run the server, the Flask server is on the port 1444. And then if I ask, so this is the IP address of the Raspberry, this is the port, and then if I ask this, I do have, it does reply all what is available. And by the way, in this case, I do have a definition at the beginning that says, well, if I have nothing, in this case, I will send the help function, and then the help function lists all the available commands. Okay, and then if I take this one, for instance, or if I ask for the current weather, in this case, I do have the same. So the reply of the system is a JSON file, so I can really I can open I can see the different parameters from the station, okay, from the weather station. So this is in real time. And then I can, the ID, so this is very useful because I can, so this system can be used between different scripts, but I can also interact myself with each script. So if I have to debug, I can just send a command and say, well, what does reply this script? Why don't I have what I do expect? Okay, I'm going very fast. Because I'm late already, and I should be the timekeeper, which is very stressful. So we can go even deeper with the system. So I can use the same system and go beyond with the Bootstrap solution. And let me show you, in this case, I do have the same, sorry, here it is. So I can use exactly the same system here, but I use, in this case, another, so this is the same IP address, but now I have a web server thanks to Flask and Bootstrap. And then I have, this is exactly the same values and the same data, but with a great presentation. Okay, so I can really debug to have the low level, and I can construct some high quality interfaces. Okay, and so again, this is just to figure out how to make all these systems working together. And now I'm close to the end. What I also want to show you very quickly is that you can make Python working with other tools, and especially for the weather station, the weather module. I wanted to have a minimal effort for the development, for the software development. And I found these different tools that are wonderful. So the Mqtt is a small message system. You can send a message and you can subscribe to the different messages. And these messages can be dispatched to different scripts or applications and so on. Telegraph is a small tool that is able to read the Mqtt, to read the Mqtt requests and send them to a database, which is called InfluxDB. And so this is a time series database and a real database, and you can ask some question to the database with the SQL commands. And behind that, you have Grafana, which is a graphic tool that extracts the database, the data from the databases. And all of this is, I didn't develop anything. I just changed some configuration files to make it work. And at the end, so I have my script that work, and I can ask any script what is what they are doing and what are the weather data. But on top of that, here is the result of my weather station, and this is the real-time system at the moment. And you can see the different parameters that are extracted from the database. Okay, so I have the rain, there is no rain. I see that the light is wonderful here, so the weather is good. I have the sky temperature with the higher sensor and so on. And I can really go and look at the seven less days, for instance. I can see the evolution of the weather and so on. Well, we have a problem with the humidity sensor, but this is a detail. Okay, this is just to show you how it works. And I think that's it. Yes, for me, this is very important to tell you, to remind you that we are doing all of this to, at the end, to take spectra. And I'm very proud because this is one of the spectra I've taken a few days ago, but the NOVA with the UVEX in the infrared part. So we are close to 1 micron here. And this is really, the goal is really to do that for spectroscopy and for astronomy. And that's it. Thank you very much. And now I give the mic to Thibault. Thank you.
Thank you very much. Okay, so I'm going to talk. So I won't really show. Oh, sorry, I won't really show code here because what I'm talking about will be scattered among different projects and many files. But I will say a bit more about what I've built to build like a robotic astronomic system with open source tools that are already available. So basically, everything that I will show here is based on existing project that I've used to integrate together to build a robotic astronomy platform. Okay, so why robotic astronomy? So most of you know that like robotic telescope exists for quite a while. They are quite, I mean, most famous, for instance, application were used for building star catalogs and astronomy catalogs of proper motion for stars, like the SDSS catalog and Gaia. Um, Quite some, I mean, there were quite some significant efforts, both from professionals and amateurs, to build transit photometry surveys, because you can do that with quite an high throughput. It was actually very interesting for me to go through all those projects that were looking at automating a set of telescopes to build a light curve for a lot, like hundreds, thousands of stars every night. There are actually quite a lot, and I learned a lot from looking at the project for which they made their automation code available as open source project. So actually, what I will present here is a tool that comes from a project called Panoptes, and it's also part of a project called UNSMAN, which is a set of telescope that runs in Australia, I think. Yeah, so there are robotic astronomy is like almost everywhere here. Something that I wanted to also highlight is Zwicky transient facility. Some of you might know this. It's a very open, like F1 or F2 telescope that publish about 100 or even more alerts every night for potential detection of like novelty detection of the sky. It can be almost everything, but like right now, I think many people are concerned. I mean, try to find novas thanks to the alert built by ZTF. In the future, we'll have the LSST that will also provide many times more alerts also. So there is an opportunity here to connect robotic telescope to those systems that will provide alerts. Okay, so what tools am I using in Python? So the project I'll talk about, and I will give a demo shortly, is synthesis of actually many projects. Here I put 12, but those are only the one that relates to like really astronomy. I will zoom a bit on some, but the important aspects are Indy. So I use the Indy, which is kind of ASCOM for Linux. There is also Panoptes, which is a open source, a set of open source project to not only drive telescope, but also database, search through the database, analyze the data. I will say a bit more about this. I'd like also to thank their amateurs that also provided very useful tool, like Serge Golovanov, that built a script that allows to provide a meaningful list of potential star for calibration when you've done your spectroscopic observation. Okay, so the very first very important tool that enables robotic astronomy here is astrometry.net. It's at the heart of most of plate solving solution out there. The initial paper was published by Dustin Lang, and my project do rely, of course, on astrometry.net to be sure that it points to the right direction. So there is pan-up test. Its hybrid was started initially by professional astronomers around 2015. The target was to publish a build guide to build the small unit you see on the bottom right. That's made of 2 DSLR with like everything, almost everything here is off-the-shelf material that you can buy, and all the software is open source, and you can use it to set your own unit and participate in this project for exoplanet detection. Here is, just to give an example, here is the interface of the search engine they provide as part of the solution. So you can get logs of all the acquisitions that have been made in the past. You see that for year 2020 there were 6 contributing units, more than 6,000 observation, and more than 200,000 total images. Okay, so I've already touched upon IndieLib. It's like basically it's really like ASCOM, but it runs on Linux and Mac also, and it's kind of the glue in between Python and your hardware. And many, as of today, there are more and more astronomy gear provider that provides you with driver for Indie. Also, I wanted to cite one aspect that is part of the future of the project I will show you, Toolkit. It's a tool that comes from professional astronomers and allows you to connect basically your scheduler to a list of brokers. So brokers are a platform that provides you with astronomy alerts. So for instance, basically you would rely on a broker to get the alerts that are generated by the Zwicky transient facility. They will provide you, for instance, with coordinates and time at which there was a potential discovery of a nova or something like this. Okay, so sorry for the slide. This one is a bit heavy, but I will present the system that I will demo today. So every time you see this small sign here, it stands for a software, so a set of Python files that are independent from the other. So the heart of the system that I will present is what I call here main application. It's basically the backend that will command everything. There is a front end server that looks somehow like what was shown just before, to basically check out what's actually happening on the robotic system. We'll provide with picture, with graphs, plots, lots of information about what's happening, and those two will communicate together with a message queue system also and a database. Okay, from the main application, like when you will have done your observation, you will send them to cloud services that you will be able to search from, or eventually apply analysis pipeline, and you can potentially plug a scheduler. That's the Tom toolkit here. So how does it work? You have your telescope and your spectroscope here. This application, of course, everything here is in Python. I have this system is meant to be quite generic. So you have classes for a guide application like PhD2, class to control the spectroscope, to control your camera, your mount, eventually your dust cap. And to all of those generic classes, I've personally connected the Indie, so a Python Indie class that glues the hardware to those classes. But the initial author of the project, they have their class with like they've implemented some they do not rely on Indie. They have implemented like all the parallel all the command they send through USB and everything for custom gear. So it's meant to be quite generic and control a lot of things. But I personally think connecting with Indy was a great asset, because now I can command and swap the gear to command different things. So yeah, this is the basic of the project. I will say a bit more about what you will see on the browser, but basically it's like Tornado. It's a Python server. There is also Python tool that helps you publish images or publish plots in a nice way. I've wrote a bit of JavaScript, but really not too much, just to customize a few things. Okay, so conclusion, let's jump to the demo right now. Main message here is that for me, like it's really good that professionals have published part of their code for their robotic observatories as open source, because it really allows to build much more efficient tool even for amateur astronomy. And that also includes like not only controlling the telescope, because of course there are many people already using tools like SGP or commercial tool like this to command their telescopes, but also everything that relates to database, putting work in common, and eventually doing big data searches among those databases. Okay, so now we'll show the interface. So this is the front end I talked to you about. So it's also built with Bootstrap. So here you see some information, showing just few information about local time, sidereal time, like how far we are from sunset, sunrise, some information about the telescope controller. So here I've connected everything to a like virtual telescope that Indy provides. An important aspect, I think, is this. So it's finite state machine that defines the behavior of the observatory. So now it's observing, so it's taking an exposure. It came from the state focusing, and if at some point it changes state, you will see here live changing on this picture. Just for you to know, this set of states is defined in config file that is here. Okay. Close. Now, if I go below, I have also something you're probably familiar with, although probably you've not seen it that way. It's basically the drift in right ascension and declination in arcsecond. That's basically the guiding the guiding performances, so you can check those out from there. Yeah, but it's basically everything that has been sent by PhD2. I'm using PhD2 right now. I'm just propagating the information up to the front end. Here it's the weather. So of course not really interesting, because I'm also using weather simulator from Indy, but I've tested that with commercially available weather station that provides the Indy driver, and was working as well. So of course here there's not much changes, but okay, on this one you will have to believe me, it works really well with whatever weather station that is compatible with Indy. Now, if I go below, I have information about the mount, where does it points to, what's the slew rate, the current track mode, and if you're guiding, like what's the configuration of the guiding. Here I recover the RTSP flow, like information, so I can control, like check out the camera if you have one in your observatory. Now getting to more interesting information. What are we currently observing? So I plan the observation with a set of config tool for now. So there might be a new solution in the future for this, but right now I'm using this. So I put a set of constraints. I want the maximum air mass, maximum, so moon separation in degree, and a set of targets that I want to acquire with priority for the scheduler. How many, how many set, like I want sets of acquisition that are at least of 2 images. I can also set the temperature of my camera if this one is as a cooler, the gain, and the exposure time. Also, you will notice that the reference for spectroscopy is chosen dynamically with basically the script from Serge Golovanov. And I just provide with like basically how many reference observation counts I want. So here, as you can see, there's a few information at what the telescope is pointing to. Here, for those that use the simulator from Indy, you will recognize this images that comes out of the simulator, and this is the outcome of the of the plate solve. So here it found that was Iota Origae, and the star that I'm going to do spectroscopy on. And here, for those that know, I've integrated Aladdin Light. It's really nice. It's a really nice JavaScript tool that provides you. So here, basically, what you're looking at, it's my pointing image. So if it was not a simulator, you would see the small slit here. And what is really nice is that I've plugged in a small JavaScript code that allows me to toggle and untoggle the pointing image and the reference catalog. So I can really check, okay, am I really at the right spot? And like normally, if everything is made, yeah, good overlap is perfect. So I'm using here Aladdin tools, and it really works well. It's really nice to use and really easy to integrate. Okay, so here again, I'm using the, here you should see a nice spectrum. However, I'm not using a real spectrograph now, it's a simulator. And right now in Indy, there are simulators for a lot of things, but not the simulator for the spectroscope. So here you only see the picture without spectroscope. Okay, and here it's simply the report of the focusing. So basically all the tool you would find in most of the tool you wouldn't find in a Sequence Generator Pro or a tool like this, you would find here. Lately, I have a small, let's say, information kind of not pop-up, but a small kind of chat that provides me with the information, with the dates, like what happened next. Okay, it's in focusing state. It has done 17 exposure. Okay, no need to refocus because it's good. So jumping to next step, which is observing. So here I have also the report from the state of the state machine that you've seen here. So that's it. Thank you very much for your attention, and I will give the mic to Valérie. Thank you.
Thank you, Thibault. Share my screen. Okay. Okay, so so we will, in this presentation, I will talk about a new project in spectroheliography, which is around a new spectrograph, which is built in the 3D. This is the Solex spectroheliograph. In fact, it's a spectrograph. You have the entrance that you put on the telescope. You adjust the grating and you have your camera here. And it is a slit spectrograph, and it has been designed and made specifically to perform spectroheliography. That means you're doing spectra of the sun. And the challenge that I have been given during Christmas was to not only to see the image and the spectra that is generated by the video, but also in real time to show the image which is built. So I'm very new on Python, but that was my first project to take me in this new adventure. So let me start by giving you some, or remind you maybe some acquisition principle on spectroheliography. Yeah. You have a spectrograph with a slit, and even you let the sun surface that moves in front of the slit, or you force the motion with your telescope, and that's what you have is a spectrum of the region that you are on the wavelengths that you are wanted to focus on, and the monochromatic images that you are looking for, which is really the end result that you can see here, is built from the intensities at the wavelengths of the spectral line center. So that means that during the acquisition, not only in Python, where we will have to control the camera, but also each time you acquire a frame, you will have to find the intensities at the right wavelengths, which mainly will be the center of the lines. So, build a table, build a column, in fact, and add the column frame by frame in order to build the final image almost in real time. So before I enter into the tools and some mechanics in Python, very basic that I enter into, let me show you how what it is in a live acquisition. So sorry for the bad quality of the movie. It was made with an iPhone, and I had the iPhone on one hand, and I have the other hand on the keypad of the telescope in order to force the sun moving in front of the slit. So you can see here in the spectra that the spectrum and the line here, it's a calcium line that you can have this is a video acquisition, the .ser file. And as you move the sun in front of the slit, that means you explore different elements of the surface. You can see the software not only show you the video on the acquisition of the camera, but also extract the intensity and build line by line the disk of the final image, the raw image of the disk. Of course, this image, you can see here, some bright spots in calcium in calcium emission. Of course, the shape of the disk is not circular. It's not a circle. It depends of the speed of your scan. That means that even after this image shown, you will have to continue the processing, and I will show you that at the end. But the purpose was really to show you that you can acquire and reconstruct the image in real time, which my dream is to be able to focus in the meantime and not focus on it's very hard to focus on the shape, on the limit of the spectrum, because the spectral line is focused internally with the spectroscope, but the focus of the telescope, it's the part which is quite tricky. So I try to do my best looking at the reconstruct image almost in real time. So that was my project. And I designed a small, very basic interface here to control the camera, as it was a sharp cap, but very dedicated to basic control for Solex. So let's enter into the mechanics here. I first start by the building blocks to control the SWO camera. There is a SDK to control the camera. Yeah, you download it. I put the link here, and I found a Python wrapper or Python binding. From Steve Marple, that was really all what I needed to control and to have my first command sent to the camera, get an image, change gain, set ROI, and so on. So this year I'm in a Windows environment, so I will not speak about how to do it with Mac and Indy. What I struggled to start with was declaring the library and the link to the window environment variable. So that's something I'm not familiar to. So, I mean, that was my main hurdle at the beginning. But after, I mean, refer to the documentation of the API for this driver. And also there is a wonderful demo file on the GitHub of Steve Marple, which I use extensively to test and control and to experiment. As I mentioned, I developed a small, very basic interface with a library, which is SpiceSimpleGui, because I didn't want to spend most of my time on the interface. I have enough with Visual Spec, and it was really very tool and basic control here. So when you control the camera, the specificity here is inside the loop of capturing the frame, and this is just some extract of the code here. So you have a big loop, you capture a frame, and at every frame, we extract here the column. You can compute with a command where is the position of the minimum in intensity of this column, which is a proxy for the center of the line. And you build line by line by exploring this the spectrum here, line by line. You put, I mean, the intensity, in fact, in a column, because my spectrum is at horizontal in order to speed up the acquisition process. So that means I have a rotation to perform. And by taking all this intensity, I put this in an array. And array by array, I mean, column by column, I mean, the disk is generated. The challenge I had to face is because, you know, I mean, as you do some processing between frame acquisition, that means that everything you do, you are slowing down the frame rate, which is not ideal. And the computation and the extraction of the minimum is not something which takes too long. Even saving the frame is not taking too long. What was taking most of the time is the way to display the image. The disk becomes with a bigger array frame after frame that takes some time. In fact, I use the library OpenCV, and the fact is that the image array, in order to fit in the window on the laptop, CV2 library interpolates this array, and this time is taking almost 30 milliseconds. So, and that's something that is decreasing the frame rate. That means that when I want to really capture the final video file, I have to disconnect the real-time display. It's better to increase the frame rate, but to control, I mean, that's something I have to accept. One important point is that even if it slows down the frame rate, what is very important is that the time between two acquisitions be constant. Because if you have a non-uniformity in or variation between the different frames, that means that as you move the sun in front of the slit, that means that you are sampling at different scale, in fact, the surface of the sun. And that produces the strange shape here that I go fast here, and as my array was adding up column and column, I mean, CV2 was having more and more time and slowing down to resize the big array. So that means that at the end, the sampling was really not good. So I did some tricks in order to always have a constant array size, and it works in fact, and that was my final trick to manage that. And I will end with the after the acquisition, what you want is a final image to share with people. And as you have seen, I mean, the shape is a little bit like an ellipse. It's maybe not correctly oriented. So there is a great tool, which is ISIS, but it's quite manual, but very powerful. But in some specific acquisition, when you have some conditions, an automatic script can be used. And I will now share my Python windows. And I will show you with the example of a file that was acquired by Christian, and this file is also available on the Solex website. So this is the image. In this case, in fact, I do not take the minimum. I really look at the shape of the spectral line, and we make a fit of this shape on a very high SNR frame in order to really be stable in the way we extract the intensity and then capture the protuberance if you have. So it's a little bit what you see before, except that this is not real time. Huh? You have in here it's in H-alpha. So as you progress in the video, you see the disk of the sun being built. You can see appearing some feature. Unfortunately, the sun right now is not having a lot of elements on its surface. You can see here a big spot, sunspot that was moving on the sun. And when you have these images, then the software is doing some processing, and after this video is about 3,000 images, so it's not too big, but it produces the final image with the shape is now correctly rounded. You correct some bad lines. We correct from transversalium, which is equivalent of flat, and some orientation if the spectrum. So that was my my project, one of my first real projects in Python, and I will now pass it to Jean-Baptiste, because he's developing some interesting tool to manipulate the video.ser file. Thank you.
Hi all. So, share screen. Comment on fait ça? Advanced. Ok, desktop on share. Okay. Is it okay? Sure, okay. So I'm Jean-Baptiste Buttet. I'm animate high school astronomy club at Lycée Lalande in France. And I would like to thank all subscribers that we have a Solex now, because we have reached our goal about 1,000 euros. And it's very amazing that we can do this. So I would like really to thank Christian for his very exciting project Solex, that I can do it with my student. It's a great thing. I really want to apologize first for my accent and then for my flow. I really think it's awful. But today was a big day. I do a lot of sports, a lot of work, and this evening it was one of my best friend's birthday. So I'm very tired. I'm really sorry. So I've wrote a little library called Surface Reader. You can install it with PyPy like this, and if you do this, you have to import it in your Python environment with these lines. So if you do this, up, so I import this, and maybe it's a little, it's not very, oh. You can do I've tried to make some helps, some documentation about this object. So you have a lot of documentation. So I think really all that I wrote is here. If you look something, if you find something wrong, say it, and I can modify it with no issues. So how you can use it? First, you have to create a file object like this. It's oops. It's very easy, and it handles header, so you can get some the file header and the length, the frame count, the width, the height, and you can move around the file and read frame with these methods. You can also move to another position if you want, and you can save it as a fit file. So it saves the current frame in fit format, and you can save in PNG file. And if the file have a queue, the queue is a metadata where each frame is stamped, so you can retrieve date of the frame at some position. And today we really used and reused read methods that read and go to next file. So I will show you how you can write a minimal cell reader code. So under Linux we have mPlayer that can handle file, but we have to re-implement it for a demo. So it's very simple. With Valérie codes, various codes, I've discovered P-simple key. So I begin to play with it. So I launched it. So you can open some file, play it, and you see there's a lot of black frames. We will show you how to remove it in a second time, and then you will see yes here, and you can see the surface playing. I will do a pause up here. Check. So when I trigger a play button, the trigger playing go to true. So the only thing I do when in the event loop of P-simple key, the only thing I do is to read a file, and you give here the frame, and here return code that is the position of the reading frame, or -1 if it doesn't work. That's all. Then you have a little code to transform frame in PNG in order to show it. So you can read but you can also write with these libraries. The only thing you have to do is to give a new trigger to true. It's a new SER file, and to create a new header. There's some a default value, so you don't have, if it's for test, you don't have to write all the header. You can, these lines are not very needed for test, but these three ones are needed. You can set image height, set image width, and set pixel depth per plane. These are the only three needed lines to make some tests. Here you can build a white frame and use a method that I call add frame. Add frame, and go to next and add one to cursor. So you can do add frame to do this. And I will show you Solex file straightener, as Valérie explained to you, in order to correct the slant deformation. So you can see here there's a slant deformation. It's not very straight. And here I will do some code. So the first thing I do is to open an existing file, Solex file. Then I do some treatment to acquire the shape of the slant, and then I create a new file with metadatas of the old one, and set image width, image height, and set pixel depth per plane. And then I go to a certain position where I know there is some information. It's not black. And so I read it, I do a little treatment to straighten the slant, and I put it in a list, in a Python list, and at the end I add frame of all the frame in my list. So I will launch it. So with Zoom, it's a little slow. Hopla. It's not working. Oh, because this one is open. So that's only 50. But you can do even better if Zoom is not working. And I will play a new the new one that I've called demonstrate line 50. Play and up. Oh, la. Oh. You can say, you can see it's it's very difficult. So you can see it's straight. It's a straight. It's straightened. So you can read file with it. You can write file. You can keep metadatas. So I will let Jean-Daniel Boutin, which is one of my students, to present what you've done as software, because you have to cut black frame before and after the sun shows in a Solex file in order to reduce the weight, for example. So I will let Jean-Daniel explain this.
Hello, I'm Jean-Daniel Boutin, and I will speak about this SER file cutter. So let's start. So I've already launched it. So the first step is to choose the file that we want to cut. So we can pick one in the file explorer. Next, we can see every frame of the file. At the left, the current frame is displayed, while at the right, we have all the controls. At the top, we have the frame number. Then we have a timeline with brackets marking the end and the beginning of the wanted file. And beneath, we have some buttons like play. So now it's going quite slow, but we can make it going faster by clicking on the double arrow. So we can see some image here. It's quite fastidious. So we can use the mouse to move the time cursor. So I will place it at the right place where we have no black frame. So I can place the beginning bracket by clicking on this button, and I will place the end bracket by clicking on the other one. So it's easier to use this. So now we can go to the next step. We can choose the location of the output file. So I will call him output point there. And I can click on export at the bottom, and it starts. I'm sorry, it's quite slow because of Zoom, but I will use this opportunity to show you some code of this software. So I've used the Save Files Reader library, of course. So here I create the output file, and I add to it as a header that I recover from the first file, and after I add each frame to this file, this output file. So the metadata are the same, and beneath you can see how I display every frame using their number. Here I read the frame of a number, and then I display it in my frame viewer. So I think that it stopped. So I will can launch it again to see that it cut it well. So I will open it again, and when I click on play, it works. We have image at the beginning and at the end. That's all. Thanks for listening, and I leave the floor to Jean-Luc Martin.
Thank you. Partage de l'écran. Partager. Voilà. Okay. Good evening, everybody. I'm going to a short presentation. Voilà. Of a work I did last year concerning a UVEX spectral database. This is a part of the UVEX 3D printing project. This project consists of producing a Cerny-Turner type spectro in a 3D printing designed by Christian Buttet. Currently, we are offering a 3D version accessible from our site. In the coming weeks, I hope we will be offering a new version, more automated, of our UVEX 4. You can see in the picture of the team of members around Christian Butte. What's the need? We wanted to compare the efficiency of our self-made UVEX spectroscopes. Obviously, there are programs that allow you to compare spectra, but the management of many files is complex and not very user-friendly. Finding a particular file among hundreds is not always easy. Evaluating the quality of an image is quick and easy, but evaluating the quality of a spectrum is a bit more difficult. The solution was therefore to create a web application accessible by team members. So the specification, creation of database of our UVEX spectra, fast spectra comparison tools, easy to use, accessible to the community of amateur astronomers. What technology to choose to build our web application? Traditionally, to design a dynamic site with access to a database, 3-tier architecture is used. You must master several programming languages. On the client side, HTML and CSS for the presentation, JavaScript for the interactive part, PHP script on the server side for the generation of dynamic pages, CGI and Python for access to the huge libraries in astronomy. But that's a lot of language to master. And the interface between PHP and Python is not always easy for non-computer scientists as me. With the use of a Jupyter server and notebooks, the construction is much easier. The only language to master is Python and SQL, of course, for database queries. The Voila server compiles the Python code and makes the Python code inaccessible. Of course, pardon, just voilà. Ici, here. Of course, I want to go into the code details. It doesn't present much interest in such a short time. Simply, I will take an example to illustrate it. The ease of solving of problem from large Python libraries, one of its strengths. The problem is how to be sure to find an object in database. For example, you have on the screen all the designation of the star Vega. There are many. I used two Sinbad database requests. You can therefore use many catalogs to designate the same object. This is a problem because we will not save all the names in our database for storage space consideration. My solution is in these few lines of code. Ici. Sorry. This part of the code concerns the verification of the identification of an object before entering the spectrum in the database. Firstly, here, this code concerns only the stars, and therefore, for the other objects, supernova, comets, and etc., there is no verification of designation, and I keep the designation of the header fits. For the stars, I make a Sinbad request here, Sinbad query object IDs, which gives me the list of designation of an object. If the list is empty, the spectrum is refused and it's not stored in the database. If the list is not empty, I get the first item in the list and store it in the database. Of course, to find an object in the database, I repeat the same query. You will see how easily we can answer this problem. Now I'll give you a little demonstration of the database. Voilà, here the code you can see in only one cell of a notebook. Okay, I launch the application here, and the design of the site is sober, but you can do some things much beautiful. But I focused on the functionalities. The first 3 tabs allow you to select spectra from different database. First, UVEX database, but I can access base database or other database. For example, here a little catalog of carbon stars. Here I can select a spectra on my computer. Here, for example. And here I can select a spectra to upload in database, UVEX database, and here display the spectra. For example, here many criteria, field criteria, object type. I can select from object type, telescope, spectro, etc. Object, name object, camera, grating, etc. I want to select, for example, Vega spectra in database, UVEX database. I select Vega query. Of course, I can change the designation, alpha Lyrae. And of course, I obtain the same result. I select the spectra, and I go to the display. I can view my 4 spectra. I have some tools. Zoom, and I can select the radiation line, voilà. And I can also select a range. I can select a range, for example, and I can calculate the FWHM with either absorption or emission. Absorption, FWHM. Calculate, and I can see more precisely in the little window the central radiation and the FWHM value. Voilà. Donc I can normalize the radiation. I can select the normalization radiation, for example. Here, voilà, and I can compare the spectra. I can select element chemical line, hydrogen, for example, helium, etc. I can control the calibration, wavelength calibration, and I have some tools to intensity shift, multiplicateur shift. Je peux effectivement décaler, shift, wavelength shift. Voilà. I can access fits its headers. Voila. If I want display my spectra from my computer, I choose this spectra, for example. I select here, and I can't. Alors, je vais deselect spectra, and I view the spectra. Voila, voila. I can use also compare with a spectral type. Bon, ici, it's not very, for example, but it's not significantly. Voila, voila. Thank you for attention. And I leave the floor to Matthieu.
Yes, thank you, Jean-Luc. I just wait.
Je vais départager.
Yes, thank you. Okay. Okay. So now, okay. So now I will talk to you about H-alpha line classification with AI. But before to talk about this, I just want to talk to you about AI quickly, because we can think AI is recent, because we can listen a lot of information about AI in the media, but it is not very recent, because it was created in 1950 with the goal of create neurons, artificial neurons like human brains, you know. But it is really interesting today to use AI because the performance of a computer has very increased, and there is also now a lot of data which we allows us to train AI, a lot of data with smartphone invention, you know, with online shopping, with a big company like Google and Amazon. And today we have some interesting tools, interesting things with AI, like vocal assistance, prediction in medicines and astronomy, like exoplanet detection, for example. I have to say I am not an expert in AI. I just very interesting about this technology, about this algorithm. And when you try to learn more about AI, you find first some information about machine learning. And machine learning, we can just say quickly, it is you give it some information to an algorithm, and it will try to make a regression, a linear regression. For example, if you give it experience in years and salary in euro from years, it try to create a linear regression, and if you give it a new experience years, it can say to you, okay, I think I can make a prediction, perhaps it is approximately this salary. This is very interesting, but if we want to play with more complex data like image, we need to go further in machine learning and use deep learning, which is a part of machine learning. You have some, we can talk about neural networks. You take an image like a dog, for example, it will take short parts of the image, give it to the entry of perceptrons like neurons of brains, you know, and on each entry we will apply some weight. The summary of weight with an activation function will give us an output, and we can give the output to another layer. So we have a lot of layers, and we can make some loop for adapt the weight here and try to make a prediction with a statistic model. And the model try to detect, okay, it is a dog or it is a cat. If we can take it some data, for example, for test, and if there is error, it can make retropropagation to adapt his model and adapt the weight. Okay, so he needs a lot of data. We have to tag it. It is a cat, it is a dog, to tell him what information is on the image. Very lot of data. And he works with it. He makes loops, and he gives us a model. If you take a new image like a cat, for example, he can tell you, okay, I think it is a cat. Okay, thank you. Or he can tell you where is a cat on the image, or make object detection or instance segmentation. So it is very interesting, but he needs a lot of data. And for me, I have not a lot of data about dog and cats on my computer, and it needs also a very powerful computer, and I have not very powerful computer. So we can use also transfer learning, because the architecture of the model here needs a lot of data. And if we give us, we take a model already trained by Google, by Facebook, which have a lot of data. You give it your personal data and make only the last layer training, and it can adapt the architecture, it can adapt the model for detect your personal data. So I use this transfer learning for, which I will talk just after. So in August last year, I think, François Cochard was have an idea, because he knows, and I like to play with AI algorithm. He knows, and Valérie Desnoux was creating a codification about H-alpha line profile. She takes some spectra in base databases and try to watch, okay, about some stars. Okay, this is emission line, this is absorption line, emission with a little absorption, and she tried to create a codifications about all this profile. And so we just make a meeting, and we decide to, okay, let's try to do a automatic classification about it. So I just create a data set. I take some spectra on base database, just one shot with a Python file. It is the algorithm I show you in the first workshop, for make query on base. And I don't want to disturb base databases, so I do it just once and give it on database on local on my computer, approximately 21,000 spectra. And I create some PNG for use in dataset. After that, I just take only 5,000 spectra and I transform it with Gramian angular difference field for best shown of intensity, and the model training is more efficient with PNG, with image like dogs, like cats. So it is more efficient with this kind of image, intensity image. So I give it to a library to train a model. The library I use is FastAI. There is two big library in AI, TensorFlow by Google and PyTorch by Facebook. And FastAI is very simple and based on PyTorch. So I use it. I use transfer learning with this library. It is approximately 10 hours of training on a Colab. And what is interesting with Colab, you can use TPU, tensor processor unit, or GPU. And it's free. So it is very interesting. And after that, it gives you a model. You can give it your personal spectra, and it can detect the line profile. Here it detects it is emission and little absorption, and you think accuracy approximately 98%. So today it works. It seems to work. It needs to be improved again, I think, with best AI hyperparameters. But what we can do with it is to take a lot of spectra about one star, and make like a time series. And perhaps with a massive processing, we can detect perhaps the changing of the profile line in the time. So today I work on this with the model I create. For share and test with everybody the model, I create also the Colab with explanation, all the steps of the trainings you can read and make again on approximately 500 spectra. It takes approximately 10 minutes to training, and it gives you a model a bit interesting. I also create a notebook for local test. You can launch on your computer on only a Jupyter Notebook or with Voila app, and you can give the model your spectra, your personal spectra, and try to detect and watch if it's good or not. And I make also online application, which is more user friendly, you know, for test, and everybody can test it online. I depose on my GitHub a dataset about 500 spectra of base for training, you know, and I propose you to just watch it quickly. I just stop it and okay, this is the GitHub. So you have the Voila, the Jupyter Notebook here file. You have the online application in just one file in Python, and the model, the inference here, export.pql, and the training folder. You can watch it for how does it works. And quite a little explanation for README in a README, and you have the dataset for training, 500 the spectra, and the collab, and here's the application in production. So the collab, you can find up. I close it. You can find so. For now, it is only in French, but the code, the commands code are in English. But I will translate it in English also for the two versions. And I just go down. You have first the file tree, and just one word here. The library and the organization of the projects can permit you to train another model. Here it is the folder on the GitHub, and you can take here it is the tag of the line profile, like absorption, little emission, little absorption, etc., and the image, the spectra. You can change here and perhaps make another tag like dogs, here like cats, birds, etc., and give some image, some picture, and in theory, okay, in theory, you can just launch training and it would create a new model with your image. So after I explain the imports, first AI, okay. Preparation of the data. Here it is the CSV data from BESS which I download by the query, you know, with fits file name, PNG file name, the header information. I want to create a clean dataset first for for not create a new dataset every week or every month. So I just want to do once clear and clean and go. The methods I show you in the first workshop for create spectra with specutils, etc. I go down for showing you the training, and this is the data set like intensity with the intensity in GADF graph, absorption, emission, little absorption, and you have all the different shape of H alpha line profile. After that, I just launch, detect the learning rate for best training, and here it is the training. So in approximately 10-15 minutes, he trains on 500 spectra and give you a model. It works a bit. It is very interesting for just test in a short time. And after that, you have the result of your training, and with the real line profile and the prediction by the model. If it's green, the model are good. If it's red, the model are not good, for sure. So you have the result and the matrix confusion between across the profile for detect if it's good or not, 0 AER and 0 AER. If it is on crossline, it is okay. Okay, this is a collab, and I create an online application for test, so you can test. Everybody can test. You have just to say if you have a fits from best database or personal fits, and you give it the fits. It works a bit, I hope. and it gives you the result of the predictions, the line profile, the accuracy, and I write a little message for user-friendly application if it's good or bad prediction based on the accuracy with color. And you have the explanation by the file of Valérie. Here you can have the explanation of the alpha line explained here, and the line. And so we can see absorption, emission, and another absorption under the continuum line. So, so that's all for me. You can play with it if you want. Don't hesitate. I go on the PowerPoint, and I have now to conclude about these 3 workshops. I just up full screen. So we have seen together first Python for astronomy and spectroscopy in the first workshop. After we have seen together Python and its environment, and today testimonials about Python. And I have to thank all of the speakers because every presentation was very interesting. And I also want to thank Olivier and François because they proposed to Vincent and myself to do this workshop, and it was very interesting to prepare it and to share it and to discuss with all of you about Python. And for the real conclusion, I just want to say Python is very interesting, but it is only a tools, and the real goal is for us is to make science for sure. So thank you for being present of all of this workshop. I hope it will be it was be interesting, and you can find all the presentation again on the Sheliak YouTube channel and all the source code Python on my GitLab. And don't hesitate for sure to contact us for discussion or questions or everything you want. It will be a pleasure for sure. Thanks to everybody.
Thank you very much. Thank you very much, Matthieu. Thank you very much to all the team. Well, I love this. I'm very impressed by the variety of applications that we can have and the variety of the competencies and the knowledge we have in the community. And this is really really impressive. And well, when we are working all together, we can really move mountains. And thank you to all of you. I see that there are a few questions, but maybe you can, if you want, if you have questions, we are not so many people online, you can switch on your microphone and ask the questions directly. Who does it first?
I put a question in the chat before. It's for Jean-Luc. I'm just curious. I've never done that for actual spectra. I was just wondering, how do you compute the FWHM? Because in some spectra, we know that the shape of the emission or absorption can be a bit weird. Can you just say a few words about this?
Pas vu la question.
So,
tu peux me l'introduire parce que...
La question c'est comment tu peux... Ouais.
Je peux la faire en français. Quand tu fais l'estimation de FWHM, tu as, potentiellement, il peut y avoir des courbes, j'imagine plus ou moins compliquées en absorption, etc. Quel modèle tu utilises? Tu fais fit une lorentzienne ou une gaussienne?
C'est un modèle gaussien, hein, c'est tout simplement. Avec une correction de la base, et c'est un modèle gaussien.
Okay, so the question was to perform the FWHM measurement calculation. What kind of profile Jean-Luc uses in the database? And he said, well, this is a Gaussian model. This is a very simple Gaussian model. And Thibault, you did have another question for Matthieu.
Yes. Yeah, it was for Matthieu. So I was very impressed by your example. It was very nice, very interesting. I had actually heard of things a bit similar to the feature transformation you use, but I know, like for instance, in natural language like spoken language identification. You have things that's a bit similar called Kepstrom. Anyway, just had a small question is whether you try to build a first baseline model before going into a deep learning model for 2D signal.
No, this is a very good question. And we talk about it with Valérie, and it was his first purpose by Valérie. I don't try it again. I think I will, because it will for sure, it will be interesting to compare it. I just try to create the data set, and after that I make some search, some try about library, and I found Fast AI, and just okay, it seems interesting. I just play with it, and it's like when you pull on the ball of the wool, you pull and the wool comes. So I just pull on the ball of the wool, and Fast AI comes, and I just play with it, and I do the model. But I think I will try to do with linear model like SVM or Forest or I don't know again, but I will try. I think I will try also for compare it. Yes.
If you allow me, just one additional question. Have you checked in the literature if this has been already attempted, or like, do you think there is even an opportunity to publish that work?
I was seeing some little things about it, but not in the same way. There is some work about B stars, but not in the same way. It was not on the actual line profile and not codification. It was all the spectra, or I don't see other works about it. I don't know. I think it is more a question perhaps for Valérie or François.
Yes, in fact, classification of shape of lines in B star has been obviously attempted and done, in fact, by professional, but their classification was meant with or was designed to classify star that has some meaningful physical parameter attached to the star. They wanted to detect the shell star or detect asymmetry, which was a classification of different type of star, which was completely different in the spirit of encoding the profile. Was really, don't think about the physics behind the star, just look at the shape of the line in order to encode the geometry, in fact. And the purpose of, I don't know, in fact, what would be the purpose at the end, but I know that for me it was helpful to extract from the database all the lines, all the stars that was always in emission, all the stars that was having a transition between absorption and emission, which was not linked to the physics of the star, not to the type of the star, the temperature, or the layers, or whatever. It was purely geometry, and that was an idea that was really fitting well for an AI, and Matthieu has did it. So I mean, it's wonderful. Now, if it's going to be useful for professional or later on, we don't know. We talk with some people, and that's mainly, as I mentioned again, it's purely encoding geometry and not at all related to the physics, and which professional papers are more aimed to understand the physics. That's why it was not seen that way.
Thank you.
Is there any other question? I see Hub, you would like to ask. Yeah, go ahead. Hello, Hub.
Very interesting, all these talks, and about the last talk about Matthieu Le Lain. This machine learning could also be applied to spectral classification in principle, right? But it will be a gigantic task because there are so many different features. But in principle, that would be probably also a very interesting tool to apply to large volumes of stars. Thank you very much, all of you.
For sure, I think it could be it can be used for the star classification. And what I've understood is what you showed, Matthieu, is that in fact the way you did organize the system, it can really be reused very simply. Just the criteria will be different for the BE shape, the H alpha shape for in BE stars. We have given some information as an input, but if we just have some examples of A star, B star, O stars, and so on, we just have to organize the data in this way and run your model. So
yes,
absolutely.
I will try. I think it is a very good example. When I think to this organization, when you change only the folders, I think the stars O, B, A, F, I think it is the best way for test this this kind of this test for showing if the model can work with another data. I think I will try when after I sleep a bit, but I will try. I will try probably.
Any other question?
Francois, this is Wayne Green. This is like for Valerie and then for Matthieu. I'm putting into the chat now a link to a textbook that it's not really a textbook. It's sort of tied into some YouTube presentations that I stumbled across from a guy named Steve Bruton at University of Washington. It goes into some of the most incredible approaches to analysis like this that turns into things like flow. He does things like compares the cat and dog thing, how to clean data, all this kind of stuff. It's a very approachable bit of information. This guy's a very lucid lecturer. And I also put the YouTube to one of his videos there. And once you get one, you can kind of find all the other ones that are going on. So what I'm doing right now is I'm using a technique called principal component analysis, which builds an eigenvector, which represents a spectrum. And this goes with a time series of spectra, 68 deep, very noisy spectra, because it was just a sample set. And what we were looking for is hydrogen alpha flares in that period of time. So and these are M dwarf stars. So how do you make a continuum for an M dwarf? Well, with PCA, what we're able to do is look just a little bit past this event, because the event occurred very early in the data set, and just assume that's the nominal continuum of the star. Bear in mind, this is an M dwarf, so it's like noisier than heck. So what we do now is that we have an approximation of that continuum. We have an error expression for that continuum. And if we subtract that from this flare event, what you get left over by definition is the equivalent width of the energy that came out of that. So this is a sample where you want data that's out of band with the actual events to build a really nice continuum specifically for that star, because that carries that star's particular physics with it. And then as you come back with well-calibrated spectra, you guys get much better about calibrating the spectra, then you can just almost print the effective width with a nice error expression for what the errors were. And this is well done by Dr. Bunton. He delves into the error as well as doing with the signals. So I highly recommend that for those guys that are really looking for a broad introduction to this, that's a good place to start. Just watch the YouTubes. I found them fascinating. Thank you. And by the way, excellent series. Thank you.
Thank you very much. I will check it.
We'll check.
Yeah, interesting. Well, by the way, we see that we could spend several workshops on the artificial intelligence. It is just a workshop about Python. Wow, wonderful. Any other questions?
Well, wait, let me say one thing about that analysis. It was about 20 lines of Python.
Yep.
20 lines of Python.
Yeah. Okay. That's it. Okay, so, well, I stopped recording. thank you very much to
you.
everybody. Thank you for your participation. Thank you for the presenters. Thank you very much to Matthieu and Vincent. Thank you also to Olivier, who is not present tonight, but he is present anyway. and talk to you soon. Thank you. Bye-bye.
Thank you.
Thank you.
Bye.
Allez, ouais, vous êtes tous restés là. Dans les,
J'ai convié Jean-Daniel à rester sur la fin.
Ouais, bien sûr, bien sûr, bien sûr, bien sûr.
Super.
Ouais, bah, c'est sympa. Bravo, Jean-Daniel. Hein.
Bah, bravo.
Ouais,
même en
super.
anglais, même pas peur. Génial, super, fantastique. Continue comme ça, lâche rien. Vraiment très, très chouette. Et très chouette présentation. Bon, moi, de nouveau, j'ai l'impression, je trouve que c'est assez bluffant tout ce qu'on arrive à couvrir. Bon, je suis un peu moins surpris que la dernière fois parce que là, on connaissait un petit peu le contenu. Ce que je constate, c'est que donc pas énormément de participants. Il y avait 24 personnes, je crois. Par contre, ils sont tous restés de A à Z, quoi. C'est du début à la fin, ce qui est quand même un signe intéressant. Voilà. Enfin, moi, je vraiment merci à tout le monde. Bravo Mathieu, bravo Vincent.
Merci à tous.
C'est une belle série.
C'était bien de revoir les présentations 2 fois, finalement. Il y a des choses que je n'avais pas vues la première fois.
Oui, effectivement.
Il y a des trucs que j'ai plus compris.
Ouais, non, mais tout à fait. C'est vrai qu'il y a des ouvertures du côté de l'intelligence artificielle. Enfin, ce que tu as commencé à ouvrir, Mathieu, là, bon, déjà, il y a d'autres personnes qui le font.
Bien sûr.
On n'est forcément pas les premiers, mais par contre, quel champ d'application monumental. Et c'est vrai que la réaction, le coup de dire, tiens, appliquons ça à la classification stellaire, spectrale, c'est génial, quoi.
Ouais.
Mais les opportunités sont juste monstrueuses.
Eh bien,
c'est passionnant.
Un bon week-end de Pâques à tout le monde.
Ouais. Et alors un timing parfait. Hein. Je crois que c'est moi qui ai été le pire dans l'histoire, là, mais même pas complètement cata. Et vraiment, c'est tout machin, chacun son quart d'heure. Parfait. Vous êtes super. Quoi. Allez, merci beaucoup. Ouais, bon week-end de Pâques, c'est vrai.
Bon week-end, oui.
Amusez-vous. Pas trop de chocolat.
Prenez soin de vous. Et puis à très bientôt.
À bientôt. Ouais, merci.
Merci.
Plaisir. Salut.
Ciao.
Un plaisir en tout cas. Merci.
Salut. Et bravo
Merci.
Jean-Daniel.
Merci à vous.
Merci.
Salut.